welcome back. Today is day 4 of our Verilog and digital design series. We are diving into the meat and potatoes of hardware description, blocking versus non-blocking assignments, and how to structure your code using module, port, and instantiation. If you want to avoid those frustrating synthesis errors, this video is for you. Blocking versus non-blocking assignment. Blocking. Think of it like a standard programming language where one line must finish before the next begins. This is perhaps the most important concept of hardware timing. The difference lies in when the right-hand side is updated to the left-hand side during the simulation cycle. We'll understand it in detail. Blocking assignments. In a blocking assignment, a statement is evaluated and updated immediately before the simulator moves to the next line. Hardware mapping usually represents combinational logic wires and gates. The trap. If you use blocking assignments for sequential logic, you can create race conditions. This is very important. We'll learn about it in the next slide. Where the order of your code changes the hardware behavior. We'll also see what is non-blocking assignment. A non-blocking assignment works inside a procedural block. When the clock head edge hits, it means if you are on a positive edge, the simulator scheduled all updates. It means at a particular positive edge of the clock, the simulator will schedule all the updates. It will not wait for one cycle, then go to the next cycle. It will not happen like that. Calculates what the new value should be and only then updates everything at once. This perfectly mimics how physical silicon works. All flip-flops sample their input simultaneously at the clock edge. The rule used for any logic triggered by a clock. If you are using a positive edge or negative edge, you can use a non-blocking assignment. We'll also learn what is a module. A module is a logical boundary. It encapsulates all the functionality so you don't have to look at 1,000 lines of code at once. So you have a module and an end module that tells you that all of the code is present within that logical boundary. A module is a block of Verilog code that implements a certain functionality. Modules can be embedded within other modules, and a higher level module can communicate with its lower level module. And they have input and output ports. They are fundamental building blocks of digital hardware, enabling modular, reusable, and hierarchical design methodology. I'll be teaching you this with an example in the next slides. Yeah. See, this is a basic design code. Module name is there, and you will put all your input port and output port. And this is your body of the code. You'll be writing about your bias register and your assign block. Either you'll be using continuous assignment or you'll be using a procedural block. Then function and task definitions, submodule instantiation. And then when you're finished writing all the code, you can put end module. This is the basic syntax. In a similar way, we'll also use it for test bench. You write the module test bench and the test bench logic, whatever the input you will be giving and what are the output that it is going to come, you can verify it using the what do you call after the synthesis you get the waveform, right? In that you can verify it. Port declaration. You use the ANSI style in the modern standard because it's much more concise. See, here input wire A is one of the port and wire B is the second port. And output wire is also a port, it's output port. Assign y equals A and B. It's an internal logic that you're writing. See, inputs always must be the type of wire. It cannot be a reg. But output can be wire for combinational or reg if assigned inside an always block. If you want to understand what is this, you can visit the day 3 lecture on combinational logic and procedural block assignments, how we have done it. Instantiation. Instantiation is very important because if you have multiple codes running, if you want to bring in a smaller block into a larger code, consider you are doing a 4-bit full adder and you want 1-bit full adder to be instantiated in the 4-bit full adder. At that time, instantiation becomes very important. Let us see the difference. You have two types in it, a named versus positional mapping. My suggestion would be you should always use named mapping because it ensures that even if someone changes the order of ports in the submodule, your top level design won't break. I'll explain this using this example. You see, this is your positional modeling. Here, you'll write it in an order. Value 1, value 2. These are your ports, right? You're writing it in order. Here, the risk is high. By chance, if this variable value 2 comes first and the value 1 goes the next, your circuit will fail silently. So what we will use is we'll use named type of instantiation. Here we put clock and assign the whatever was there in our lower level module. Similar way, your D is given as input. So the risk becomes very low because you are telling this connection will go to this using my higher level module to my lower level module. So the connection of the ports will be assigned to your local signal. And as in day 3, we discussed the golden rule. Today also we have some golden rules. Whenever you have combinational logic, always at start, you will be using a blocking assignment. At the same time, if you have a sequential logic, always at positive edge of a clock, you will be using a non-blocking assignment. Assign. Never assign a value to the same variable in two different always block. The hardware won't know which wire to listen, resulting in a multi-driven net error. It means if you have two always block, don't use the same name for it or the same wire name. That time the it will not work as hardware. That time you'll get multi-driven net error. See, this is the example using a combinational logic ALU style. Here we'll understand what is happening. Okay. Here you have set a temporary variable which is giving an output of A and B. That means it is giving the multiplication of A and B. Here what happens is temp is updated immediately because you are using a blocking assignment. And out, whatever this value of temp is there, no, it will come here. So whatever you are doing or here, that will result as an output. So what happens is at these two things will happen at a different, we can tell at a different clock pulse. So if this is happening at the first clock pulse, this will happen at the second clock pulse. So whatever this temporary variable is there, this is getting updated. Then it will come to this output. We'll see the danger also. If you use the sequential logic, you can create a race condition. Imagine this is a flip-flop and you are using multiple flip-flops in your code. That time what will happen is both will get updated to a new value and the second one might accidentally grab the new value. It means whatever the first flip-flop had a value, this might come to the second flip-flop. This will make the shift register skip a beat. So it will not work properly. See, here I'll explain it in detail to you. We have a D flip-flop, we have the input clock and input D, and output is reg Q. Whenever the positive edge of the clock is, it means if your clock cycle is 1, whatever was in your input will go to the output. Now I'm building a shift register. I want two flip-flops. I have instantiated it properly, I've given the input. Now what happens here is, this race condition happens. If I am using a blocking assignment, if I write only Q equals to D, here Q is all at the stage 1, Q is equal to D. So whatever was in D will come to Q, right? Then the Q value changes. Again here it is not getting updated. The same race condition happens. So you will be getting the same output again and again and again. That should not be happening. So when we use non-blocking assignment, at the same clock cycle, both the flip-flops will get updated. Then we have multi-stage counter. Here see, why I am explaining this is, here we are going to learn about sub-module and top-level module. Whatever system that we are using here, see, I have designed a counter here. So if you know how a counter works, at every positive edge of the clock, if your reset is not equal to 1, the count is, if your reset is equal to 1, count becomes 0, 0, 0, 0. That means your count is reset to 1. If it is not a 0, at every positive edge of the clock, the count is incremented. This is your counter. Now I want that counter to be put in a device where I want LED as the output. So every time there is a counter, the LED blinks. If that is what we are doing, here I take this counter module, I put it in my top level code. So this is a LED blinking code. Whenever my counter is incrementing, LED will give an output. So this is how smaller modules are used in top level modules. Thank you. If you have any doubt, feel free to put it in the comment section.